this talk, and we look forward to your talk.
Oh, thank you very much, Ali and everyone, and thanks for the pleasure and privilege to just share some thoughts here. And then at the end, like Ali said, we can take questions, and hopefully everyone can see the screen and the slides okay and hear me okay. If not, stop me.
Everything is good, thanks.
Perfect. So just a quick acknowledgement. The material presented here is based on some work that was done by Peace for AMO a few years back, and they graciously allowed me to share some of the high-level stuff. So I'm grateful to them, and particularly to Dr. Nilesh Modi, who was instrumental in the work and provided some great sort of leadership and advice along the way. So that said, let's kind of talk about it. And as I say, I'm kind of using material based on that work at a high level. So the background question here was, and like Ali said, the presentations around, impact of IBR's grid forming and following, both on small signal stability. And in this context, specifically, and most of the times that is the context today at least, is how could they possibly impact these electromechanical modes of synchronous rotor generator oscillation, particularly inter-area modes. And we're all familiar with those. Just maybe take one step back to kind of define that so we're all on the same page. This is something we've known for decades and decades. The original papers were by folks like DeMello and Concordio in 1969 on this whole concept of when you have synchronous generators throughout a system, like any dynamic system, you'll have modes of oscillation between these synchronous plants. And some of these modes will be between large groups of plants oscillating against each other. So like in this example of the Australian network, you have these large areas, Queensland. Let me see if I can get the pointer to work so I know you can see me. So we have like Queensland, New South Wales, Victoria, South Australia, and then snowy mountains in the middle here. Tasmania is connected through a HVDC link, so it doesn't really come into the context of what we're discussing here. But you could have generators in, say, Queensland oscillating against the rest of the network, or generators in South Australia oscillating against the rest of the network. These are inter-area modes. And here we're talking about, because there's still synchronous generation in grids like Oz and everywhere else in the world, these modes still exist. And historically, in systems like Australia, these inter-area modes have been very lightly damped. Some can potentially even go unstable under certain operating conditions if you don't have properly tuned power system stabilizers. So the question is, as you replace some of the synchronous generation with renewables, and as we put IBRs into the system, can these IBRs be effective in helping to dampen these inter-area modes? Particularly the question in this context was on BESS, battery energy storage. And does it matter also what type of grid? Is it grid forming or grid following? Is one better than the other for doing this kind of damping, or does it matter? And what are other influencing factors? So those were the questions that we're going to try to dive into here. So here were the specific tasks in the context of that work. So we took several different types of BESS, and these were detailed vendor-specific models, and we developed the small signal, sorry, I should have spelled out the acronym here, small signal stability model. So and I'll talk about that in a second, what that means. This is forming an explicit small signal model, so state space model, for these grid forming converters and these grid following inverters. So we took both types and we develop those user-written models in a software package. In this case, happened to be SSAT, PowerText software package. There are other packages you could do this in. And then to take those and go and deploy them in different parts of the network and see how they affect small signal stability, specifically damping these interior modes. And are there opportunities for putting a power oscillation damper on these to enhance or improve the damping of some of those modes? And without loss of generality, we'll talk here about a simplified Australian model, but it's the same concept whether you apply it on a reduced order model or a large model. It's still the same thing. And when I say here simplified, I don't mean that the models are simplified. I mean, rather than modeling the entire Queensland grid in detail, this may be a half a dozen buses with some large aggregated synchronous generators and so on and so forth, so that it's a reduced order in that sense, but the models are still these detailed, in many cases, vendor-specific models and so on and so forth. So we took that and then decided on deploying both GFM, so GFM being grid-forming inverters and GFL being grid-following inverters. And I'm sure you all know what that stuff means better than I, but just again to make sure we're on the same page. By the grid forming, we mean the control strategies that focus mainly on voltage and frequency control, so they're not tightly controlled current in the transient time. There's some leeway there to give you great gain margin, whereas in the grid following inverters, it's the classic stuff that we see deployed today and has been for decades, where it's a very tightly controlled current regulated device. And then we deployed that at various places throughout the network and tested some large number of scenarios, and talk about that in a second. But here's some examples of how the grid looks, kind of this longitudinal long grid that goes around the coast of Australia, some maybe 3,000-4,000 miles. And these days I think miles should be talking kilometers because it's Australia. And so you've got this longitudinal system, and you deploy these BESSes at various locations along the system, at system boundaries, close to load centers, close to generation centers, to see both the GFM and GFL and play with it to see how it might impact these various inter-area modes. So we looked at 3 base cases, different power flow conditions, 4 different BESS locations of 2 different types, and 6 different options for stabilizing signals and stabilizing controls, looking at things like measuring bus frequency as a stabilizing signal and putting the power oscillation damper at the power plant controller level, or measuring bus frequency and putting it at the inverter level, measuring bus voltage and putting it at the PPC or inverter level, and then measuring tie line flows on major interconnectors where you get a lot of the power oscillations during inter-area modes, and locating them there. And again, either on the PPC or at the inverter level. And again, just to step back a second, it's probably obvious, but just make sure we're on the same page. The PPC being the power plant controller that sits on that particular power plant, in this case being a BESS, and regulating all the inverters, whereas the individual inverters have their own electrical controls right there local at the inverter. So that's what I mean by inverter level controls, right? So there was quite a number of cases, and did full eigenvalue analysis on all these cases to try to look at the sensitivity of the different control strategies, different places you put the controls, different type of inverter technology, to see if we could see some sort of pattern developing of what influences their effectiveness the most. And so let's take a sidetrack for a second on the POD, or the power oscillation damping tuning technique used. Now, obviously, there's surely numerous methods. Literature is full of different tuning and control strategy methods. So this is one approach, not saying it's necessarily either the best approach or what have you. It's one approach. It's based on research actually was done in Australia years ago, and it's based on a solid theoretical basis. So it comes from a solid theoretical basis. And I'll talk about some of that a little bit here, but you can go to the references for more detail. And it can actually be related back to the concepts of synchronizing damping torque that originated in DeMillo and Concordia's paper of 1969. So all I'm trying to say is it's a robust method based on some solid theory, but of course it's not the only method. So let's just take a step back for a second. We keep saying small signal. What do we mean? So, in our power system models, we always have these combination of differential equations and algebraic equations to formulate the entire network model. It doesn't matter whether we're in EMT, positive sequence, phasor domain. It's always a set of differential equations plus a set of algebraic equations that set the boundary conditions. And the only difference when we go from, say, an EMT model to a positive sequence model is, for example, in EMT, even the lines and the capacitors and everything is still differential equations. Everything's differential equations. They're frequency domain models for transmission lines. If we come to a phasor domain model, all that stuff goes into the algebraic equations because we assume they're lumped constant impedance values. So the inherent nature of the equations is still the same. We've got differential equations and we've got algebraic equations. Now, when we talk about small signal, what we do is we linearize those equations at a given operating point. That's why you see these little deltas. So what we're saying is we've linearized all those differential equations that were originally x equals a times x plus b times u, where x is the vector of all states, u is the vector of all inputs, and y is the vector of all outputs. And I'll say in a second what I mean by those. And then your A, B, C, D matrix are the state space matrices that relate, the states to the states themselves. The derivative of the states to the states themselves and the inputs, and the outputs to the states and the inputs, right? And so now let's talk about what each one of these things are. So in the context of the power system, states are things like, the flux dynamics of a machine, its speed, its rotor angle, or in the case of inverters, the various states of the control logic inside the converter. Like if we're talking about, in these cases, the GFMs were virtual synchronous machine GFM, so it'd be all the states associated with that virtual synchronous machine model inside the converter, plus its current and voltage and frequency regulation control loops, etc. The inputs would be all the reference inputs that are coming into all our controllers, our IBRs, our voltage regulators on synchronous machines, our governors on synchronous machines, etc. Or our inputs to our power oscillation dampers, so on. And then outputs would be, well, what we see out on the network. Electrical power coming out of each generator, reactive power coming out of each generator, power flows on lines, frequency of the network, these things. These would be our outputs. That said, one thing we should almost intuitively realize from the beginning is that in a power system context, the D matrix is always 0 because there's nothing that directly links an input to an output. There is no inputs I can put in the context I just defined that will instantaneously change an output, right? So D is usually 0. So all we're dealing with is A, B, and C matrices. So we linearize those. And once we linearize all that stuff, go to the reference, trust me, you can do a bunch of fancy math, and I'm not going to sit here and do it. Most of you could probably do it faster than I could, but I've done it in the past, and here it is. You could do a bunch of fancy math and convert this essentially state space, linearized model into a set of matrix transfer functions that hook up and look like this. This just, for me anyway, is visually more appealing because now we can see here directly. Look, these are some of our inputs, AVR inputs of voltage regulators on synchronous machines. Here are some of our, outputs, and also states like the speed of machines, or here, this might be the electrical power output of some, device on the grid. And then here, these ones are the controllers and the devices that are active devices like IBRs, HVDC, STATCOM, so on. And again, those may have voltage reference inputs. There may be other inputs we haven't shown here. And so all this stuff now comes together. What's the value of putting this diagram together? It's really this. We can kind of cut and divide this diagram, get some physical understanding of what's going on. And if you look at it on the synchronous machine side of things, the classic way to tune a PSS. So here I've put this little function up here calling it a PSS. Is the idea of a PSS is to induce a component of electrical torque on the shaft of the machine. So here on this shaft equation that's in phase with speed. So we're trying to get a component of electrical torque here that's in phase with speed. So it's easy to see that what we need to do is make this transfer function the inverse of this inherent characteristic of the machine. And then we get a direct path through here to electrical damping torque. And the interesting thing is, if you look at it the way we've divided and chopped this up, this inherent characteristic of the machine is dominated literally by the characteristic of the machine, the electrical characteristics of the generator and its AVR, an excitation system. It only has secondary impacts from the network. On the other hand, if we look at these stuff down here, the power electronic devices, so your fax, your IBR, your HVDC, etc., the only way to dampen these electromechanical modes ultimately is to, again, induce some sort of damping torque on the shafts of the machine. And there's a path here, but the path goes through the network. So there is, because these things don't directly participate in these modes that are dominated by the synchronous machines. So why this is interesting is because it already tells us that the network topology has some big influence on how we are going to have to tune this damping controller. Whereas in the case of the machine, it doesn't. That's why we can tune a PSS on a machine without really knowing necessarily what's the network out there. But that's not necessarily true for these power electronic based devices. And again, I emphasize the focus here is electromechanical modes of rotor oscillation synchronous generators. I'm not talking about modes that are dominated by these controls themselves. There are modes down here that are dominated by these controls themselves. Those are obviously things we can control locally, and I don't need to know what the network topology is. That's a different story. So now, if you kind of go through the math of all that nonsense, one of the things you can do is you can calculate what are called residues. That's what this R defines. So I can calculate the residue using a standard small signal stability tool. Once I've developed this explicit small signal model and created my user written models and put all that stuff together, I can calculate the residue from some stabilizing signal that I pick. So for in this example, maybe I'm picking the flow on some tie line, I can calculate the residue for a given eigenvalue. So that eigenvalue may be my inter-area mode of interest. I can calculate the residue for that given eigenvalue. So see eigenvalue I from that given stabilizing signal output of the model M to a given input of a particular controller. So in this case, it may be my best GFM that I want to control at the inverter level, N. And once I calculate that residue, you can show through just some simple mathematics, and again, you can go to the references for the details, that so as long as I keep the product of that residue and the first order derivative of my POD function to the eigenvalue much less than 1, and that, trust me, can easily be done by selecting this gain appropriately, then what happens is this equation reduces to this, which basically says that if I can tune a transfer function such that the phase of that transfer function together with the phase of the residue results in a total phase of 180 degrees, then what does that mean? That means a left shift in the state space domain. In other words, a dampening of that eigenvalue. So I can use that as a means to now tune my POD. And so that's the concept we used. And you can actually prove that that concept at the end of the day, because you can calculate those residue components through this, generalized matrix representation of the power system, you can actually mathematically prove that at the end of the day, that basically boils down to what you're doing is you're inducing damping torque on nearby synchronous generators. And that's how you're effectively dampening that inter-area mode. Because at the end of the day, remember, inter-area electromechanical modes are modes of the synchronous machines. And so we used that approach and we picked a whole bunch of interior modes that are very critical in the grid, like Queensland versus South Australia, Victoria, South Australia versus Victoria and New South Wales, and Vic versus New South Wales and South Australia. And we went ahead and did all those like 200 or whatever operating cases and different scenarios and ran them all. And I'm not going to sit here and go through hundreds of cases. What I want to do is bring the high-level conclusions that were extracted from those results, and then we can maybe go into the Q&A and discuss further. So both the grid following and grid forming batteries, even without a POD, could have some influence on the inter-area modes, and in some cases could actually significantly improve the damping of some inter-area modes, highly dependent on where they were located. So the location of the BESS was very important to whether it was influential on a given inter-area mode or not. And again, I remind us back to this, I know somewhat theoretical diagram, but that's intuitively now kind of clear to us, because remember, we have to go through this path of the transmission network. So all it's saying to us is, depending on what this path is, if it's so far away from the influential machines versus it's close to the influential machines, obviously it makes a difference. The same thing is on the size of the BESS, obviously it also makes a difference, right? Then when you added the POD, you could indeed further increase the damping. However, that depended on a number of things. One of them was where you implemented the POD. At the inverter level, is probably in some cases, if not most cases, more effective than the PPC because of the communication delays. Now, if you think about the nature of small signal stability modeling, you can't really small signal stability model, at least not effectively. You have to make certain approximations when you want to model things like delays. So we didn't have the best of means of modeling it. So I just caveat that the communication delays at the plant level weren't really captured in detail and hard to capture, but you could see that it does make an influence or have an effect. And again, that's probably intuitively obvious, but it's interesting to observe. The choice of the stabilizing signal obviously made a difference. The other thing was, POD tuning for the best, obviously it requires some level of compromise, because sometimes you would find that if your POD tuned a best for a given interior mode, it might help some of the other interior modes, but then sometimes it might slightly, degrade, or not degrade damping, but change the frequency of some of the local modes. So you need to really look at various operating conditions and look at all the potential negative effects to find an optimal solution. This, again, clearly indicates that to tune a POD, you need detailed knowledge of the entire network. This is something that, I don't know, may or may not come as a surprise to some, but this is one thing that was very clear, and this is one reason that you can't really, in the same way that, for example, many standards say, oh, thou shalt have a PSS on a synchronous machine. That's not necessarily a problem, because, again, if we come back to this diagram, synchronous machine, how you tune the PSS is driven by the inherent characteristic of the machine. You don't really have to have a great understanding in the network. That is not true in the case of an IBR. And so you can't really say and demand, oh, you need to have a POD on every IBR, because without an understanding of the network, without an understanding of where it's located, its size, you can't really understand if a POD is going to be effective or not. So it's not something you can require as a standard. And then, multiple BESSes obviously are going to be much more effective than single BESSes. So some of this stuff may seem somewhat intuitively obvious, but it's good to codify it and understand it from a theoretical standpoint as well. And then, just kind of very high summary, BESS alone can improve, as we said. Effectiveness depends on location, size, stabilizing signal choice, and whether you put the POD at the inverter or PPC level. The effectiveness of the stabilizing signal also has to be understood through operating conditions, and then the tuning really requires detailed network understanding. And I said this conclusion when we were looking at the previous slide, but really to understand that in the context of BESS, and I think we can generalize this to any IBR, we can't really require POD controls. We have to be able to justify it on a case-by-case basis, depending on all these factors. What's its size? Where is it located? Can I get a stabilizing signal that's effective where I'm at? And then not forget that in many cases, it may just putting it there help to improve. Well, and that's really it. I think those were the slides. That's what I wanted to cover. So maybe now we can take 10, 15 minutes of questions, if that's okay with everyone.